Okay, so now let's do one example for entropy rate balance equation. Here we have a steam turbine. We always use a diverging duct for steam turbine because what happens in a steam turbine is an expansion process. And we know the working fluid is water. Inlet is number 1, outlet is number 2. We know P1 is 30 bar, T1 is 400 Celsius, and V1 is 160 meter per second. At point 2, we know the phase of the water is saturated vapor, which means it's point G. T2 is 100 Celsius, and V2 is 100 meter per second. We also know W dot CV over M dot is 540 kilojoule per kilogram, and this number has to be positive because turbine generates work. Generating work must be positive. And the system is at a steady state. We know the temperature of the turbine is 350 K. Essentially, this is what? Temperature of the boundary. TB is 350 K. What we're looking for is first, sketch the process on a T versus S diagram and look for sigma over m if the system is adiabatic. And part 3, look for sigma over m again if the system is not adiabatic. Sigma is called entropy production. It tells us how irreversible this process is. Okay, so let's start from part 1. Sketch the diagram. On a T versus S diagram, be careful here is lowercase s. We always sketch the vapor dome first, just like before. And then on a T versus S diagram, we have constant pressure lines. Curve up, straight, and then curve up. And then let's sketch two of them. One for P1, the other one for P2. Okay, so which one should we use for P1 and which one should we use for P2? P1 to P2, which one's bigger? P1 is 30 bar, and then what happens in a steam turbine is an expansion process, so pressure must go down. So P1 must be higher than P2, so that's why the top one should be P1, and we know it's 30 bar, and the bottom one should be P2. It must be lower than P1. Okay, so now let's locate point number 2, because point number 2 is really easy and it's already given. Point 2 is saturated vapor, so point 2 must be on P2 line and it has to be G point. So G point is here, and that's my number 2. That's my point number 2. Okay, next, let's locate point number 1. Locating a point, essentially you're asking yourself, what is the phase of the point? What is the phase of point number 1? Do we know that? It's not given, but we can easily find it from P1 and T1, just like what we did before. We go to the table, we start from pressure P1, 30 bar, and we look for the corresponding saturated temperature. If the actual temperature with T1 is even higher than the saturated temperature, then point 1 has to be superheated. So let's double check if it is true. If we start from pressure, that will be table A3. If you start from temperature, that should be table A2. And if you look for superheated water vapor, that's table A4. We start from P1, which is 30 bar. And you go to the table, you can find the corresponding saturated temperature. T sat 1 is equal to 233.9 Celsius. And then my actual temperature T1 is 400 Celsius. So obviously my actual temperature is even higher than saturated temperature. That means point 1 must be superheated. Okay, so now we know the phase of point 1. Is that enough for us to fix the location of number 1? So we can take a look. Let's sketch a vertical line across number 2. If I put number 1 here to the left of this dashed line, does it satisfy the requirement to be superheated? Yes. Can I also put number 2 right? Can I put number 1 right above number 2? Does it satisfy the requirement to be superheated? Yes. Can I put number 1 to the right side of number 2? Here. Yes, it also satisfies the requirement to be superheated. So now I have three possible solutions. To the left, vertical, or to the right. So to the left or to the right, what should you check? You should always check x coordinate. Up or down, what do you check? You check the y coordinate. So we need to find S1 and S2, and how does it change? Or in other words, we need to find delta S. Delta S. If S becomes bigger, then 1 to 2 should be skewed to the right. If delta S is equal to 0, that means S1 equal to S2, and then it should be a vertical line. And if S2 is less than S1, then this line should be skewed to the left. And if S2 is greater than S1, then this line should be skewed to the right. We have three possibilities. Okay, so now we just need to find delta S. Delta S. How do we look for delta S? We can start from entropy rate balance equation, but make sure you choose the longer one because we have two versions. Take a look here. The short one is for closed system, and the longer one is for a control volume. And in our case, we do have a control volume, so we choose the long version. Derivative capital S over dt. Right hand side is sigma j from 1 to n q dot j over tbj plus sigma dot plus sigma m dot I lowercase si minus sigma m dot e lowercase se. Now let's simplify this equation. First of all, the system is at steady state, so left hand side goes to 0 because no property should change over time, and entropy is a property. And then the first term in the right hand side also goes to 0. Why? Because the first case is adiabatic, meaning there's no heat transfer. If there's no heat transfer, Q must be 0. So this equation becomes 0 equal to 0 plus sigma dot plus, okay, we only have one inlet, so it's going to be m dot S1. I don't even need to give m dot 1 a subscript. Why? Because mass flow rate must be conserved since it is at a steady state. M dot 1 must be equal to M dot 2, and if they're equal, there's no need for me to use a subscript. We do the same thing, subtract M dot S2, which is the exit. Okay, so now we can rewrite this equation. We can move S2 minus S1 together to left hand side, and then right hand side will just become sigma dot over M dot. Okay, so we know m dot mass flow rate must be positive. What about sigma dot? Sigma dot is entropy production rate. And we know if sigma is equal to 0, that means the system is reversible. If sigma is greater than 0, that means the system must be irreversible. And if sigma is less than 0, that means the system is impossible. And we have this design running okay, so it must be possible. And for anything in this world, it must be irreversible, meaning sigma must be greater than 0 for any reality in the world. So numerator must be positive and denominator is also positive. Then we must say S2 minus S1 equal to sigma dot over m dot. The whole thing must be positive. So we can say S2 must be greater than S1. If S2 is greater than S1, that means the x coordinate, which is S, is becoming bigger. x coordinate becomes bigger, then 1, 2, 2 must be to the right. Our conclusion is 1, 2, 2 must be to the right because the x coordinate becomes bigger. So now we can connect 1 to 2, and which case is our one? This one has to be number 1, so that 1 to 2 is to the right. The other two is not possible. Okay, so now this is our diagram. 1 to 2 must be skewed to the right. Okay, so this is part 1. Next one, part 2, look for sigma over m. Look for sigma over m. So we already found sigma dot over m dot is equal to S2 minus S1 from part 1, and part 2 is to look for sigma over m. What is the relation between sigma over m and sigma dot over m dot? Just like before, they must be equal. We can prove that. The definition of sigma dot is sigma over time. The definition of m dot is m over time. And you can see we can cancel out the times. What is left is sigma over m. And sigma over m is exactly what we're looking for. So now essentially we're just looking for S2 and S1. If we can find S1 and S2, then we can find sigma over m. Okay, let's start from S1. Let's start from S1. If you're looking for a property, the first thing you should always do is to identify the phase. So now let's take a look at our diagram. What is the phase of point 1? Point 1 is to the right side of the vapor dome, so point 1 must be superheated. And if it is superheated, you have to go to table A4. Okay, so now we know we must go to table A4. And how do we use table A4? You have to have two inputs, and one of them has to be pressure. So do we know pressure P1? P1 is actually given, it's 30 bar. And we just need to have one more input, and that is T1. T1 is 400 Celsius, which is given. And from table A4, you can easily find entropy as 1, which is 6.9212 kilojoule per kilogram per Kelvin. And from the table, I also write down H1 even though I'm not looking for it at this moment, but I might later. So I also write it down the value of specific enthalpy. It's 3230.9 kilojoule per kilogram. So now I'm done with S1. Next one, I'm looking for S2. And again, we need to first identify what's the phase of number 2. Number 2 is G point, saturated vapor. So essentially, you're looking for SG. How do you look for SG? That depends on what you know. If you know temperature, you start from table A2. If you know pressure, you start from table A3. So what do we know about number 2? We know T2. T2 is given as 100 Celsius, so that means we go to table A2. And our input is temperature, which is 100 Celsius. And from the table, we can easily look for Sg, and Sg will just be our S2 because point 2 is point G. From the table, the value is 7.3549 kilojoule per kilogram per Kelvin. And I'll also write down Hg, which will just be my H2, even though I'm not looking for it at this moment, but I might later on. So I will also write down this number. It's 2676.1 kilojoule per kilogram. So now I have S1 and S2. I can just plug in those two numbers back into this equation, and I can find sigma over m easily. Sigma over m is equal to S2 minus S1, and S2 is 7.3549 minus S1, 6.9212. Solution is 0.4337 kilojoule per kilogram per Kelvin. And like we said, the solution is positive because sigma will always be positive for any reality, and m will always be positive, so the solution must be positive. Okay, so that's part 2, sigma over m. And then part 3. Part 3. What is part 3? Part 3 is to look for a sigma over again, but this time the process is not adiabatic. So heat transfer is no longer 0. Okay, so what we do is the same. We start from entropy rate balance equation for a control volume again. Left hand side is ds over dt. It's capital S here. Right hand side first term is heat transfer sigma j from 1 to n. Q dot j over tbj plus sigma dot and plus, we only have one inlet, so m dot s1. And the same reason why we do not add a subscript to mass flow rate, because it is steady state, doesn't change. Minus m dot s2. Again, left hand side goes to 0. The reason is still the same, because the system is at steady state. No properties change over time. And then last time we canceled the first term in the right hand side because the process was adiabatic, meaning there's no heat transfer. But for part 3, this process not adiabatic, so we have to keep this term. Okay, so left hand side becomes 0. Now let's do right hand side. Okay, so what about TBJ? TBJ. TBJ is constant. TBJ is equal to a constant, which is just the temperature of the turbine. B means boundary, and is given as, what is the temperature given? Here, 350 K. So we can write it down. It's 350 K. If it is constant, what can we do? So that means when you do the sigma, every term has the same denominator. If every term has the same denominator, then you can just combine them. So they have the same denominator, which is TB, and you just sigma up all the numerators. Sigma Q dot J. And what is sigma Q dot J? The total heat transfer for the whole system. And then we can just write Q dot. That's it. Q dot is the total heat transfer for the whole system. And then let's copy the second term, sigma dot, and then combine the last two terms, take m dot out of it, so it's S1 minus S2. Okay, so because we're looking for sigma over m, so what we do is to move sigma dot over m dot to the left hand side alone, and everything else in the right hand side will just become negative 1 over m dot times q dot over tb, and then plus s2 minus s1. So this step is purely algebra. And we know sigma dot over m dot is just equal to sigma over m because the two t's cancel each other. Okay, so what we need to have is everything in the right hand side. S1, S2, we already found those two terms. And then what we know about TB, TB is given, constant, 350 Kelvin, like we said. What we don't know is just heat transfer per unit mass. We don't know Q dot over M dot. If we can find Q dot over M dot, then this problem is solved. How do we look for Q dot over M dot? Essentially, you're looking for heat transfer. You're looking for heat transfer. What goes to your mind? I'm looking for Q dot over M dot. If I can find this, the problem solved. Q dot over M dot, obviously we've been doing this several times. You go to first law. Okay, because it is a control volume, so we have to use the long version of the first law, which is Q dot minus W dot CV plus M dot times H1 plus 1 over 2 V1 squared plus GZ1 we only have one inlet, minus m dot h2 plus 1 over 2 v2 squared plus gz2. And right hand side will still be dE over dt. Right hand side goes to 0 because of steady state. What else can we cancel? Potential energy. mgz1 minus mgz2. The height doesn't change, so the potential energy can cancel. Okay, so now we're looking for q dot over m dot, so we perform algebra. We move q dot over m dot alone to the left-hand side, and everything else to the other side. It becomes w dot cv over m dot minus h1 minus h2 plus 1 over 2 v1 squared minus v2 squared. Okay, let's take a look. If we have everything in the right-hand side, then we're done. Okay, first of all, w dot cv over m dot, is that given? Let's take a look. M dot over m, w dot over m dot is actually given 540 kilojoule per kilogram. So yes, we can have that. H1 and H2. Did we find H1 and H2? Actually, I did. So H2 is right here, and H1 is right here. So I did find H1 and H2. And V1, V2, they are given, so I have everything in the right-hand side. But when you deal with a long equation like this, with so many different variables, what you need to do is convert everything to SI unit. Then you will never have a trouble. Okay. W dot CV over M dot is given as 540 kilojoule per kilogram. So convert kilojoule to joule by multiplying 1000. And we should plug in a positive number because the system generates work. Generating work, the work must be positive. Okay, minus H1. H1 is 3230.9 kilojoule per kilogram. So again, multiply by 1000 to convert kilojoule to joule. Minus H2, 2676.1 kilojoule per kilogram. Again, multiply by 1000 to convert kilojoule to joule. Okay, plus 1 over 2. V1 squared, V1 is 160 meter per second, SI unit already. Minus V2 squared, V2 is 100, SI unit already. So now the solution is negative 22.6 times 10 to the third. What should be the unit to my solution? It must be the SI unit. SI unit is joule per kilogram. So our solution is negative. That means your system loses heat, which makes perfect sense because in reality, you have very hot steam going in. So the hot steam will inevitably lose heat to the environment. So your solution must be negative, meaning the system loses heat. Okay, so now let's go back to our equation. Do we have everything now? Did we just find Q dot over M dot in the red box? Yes, I did. So now I have everything in the right-hand side. I can easily find sigma over M. The equation we did before was this one, negative 1 over TB times Q dot over TB divided by M dot. Q dot over M dot plus S2 minus S1. So I have everything on the right-hand side now. First of all, 1 over TB. TB is given as 350 Kelvin, so use SI unit. Multiply by Q dot over M dot, I just found it as negative 22.6 times 10 to the third SI unit, perfect. Plus S2, S2 is 7.3549 kilojoule per kilogram per Kelvin, so we need to convert kilojoule to joules. And then S1 is 6.9212, again, kilojoule per kilogram per Kelvin. We need to convert kilojoules to joules by multiplying 1000 again. So finally, our solution is 0.498 times 10 to the third. The SI unit will be joule per kilogram per Kelvin. And then we can do one more step to convert joules to kilojoules. Our solution is 0.498 kilojoule per kilogram per Kelvin. That is our solution. And our solution is positive again, which makes perfect sense. Why? Because sigma has to be positive for any reality in this world. And the mass will always be positive. So if the numerator and the denominator are both positive, your solution must be positive.